University of Georgia, who talks on arithmetic functions. Please.
Okay, so I want to begin by thanking Mel for the chance to speak. Everything I'm saying is joint work with two young mathematicians who I believe are actually in the audience. So Noah Leibowitz Lockhart, who is a PhD student of mine, he got his PhD in 2019 at UGA, and Akash Singh Haroy, who will actually be doing a PhD at UGA starting in the fall. Okay, so here is Noah on the left and Akash on the right. Okay, so this talk is about uniform and weak uniform distribution of arithmetic functions. I think it makes sense to start with the uniform distribution part because that's the easier part to motivate. So I'm going to suppose I have an integer valued arithmetic function, by which I just mean a function from the positive integers to the integers. If Q is a positive integer, I'll say that F is uniformly distributed mod Q or equidistributed mod Q if for every integer A, the limiting proportion of n for which f of n is a mod q is 1 over q. So 1 over x times the cardinality of the set on the left-hand side should tend to 1 over q as x goes to infinity. Okay, so a trivial example would be the identity function n maps to n. This is equidistributed mod q for every q. A more fun example, although not so important for this talk, is the function where n maps to the nth Fibonacci number. In that case, one can show, this is not completely trivial, that this is equidistributed mod q precisely when q is a power of 5. Okay, so I said these two examples are not so important for us. Let me move to one that is. So I'm going to define a capital A of n to be the sum of the prime factors of n counted with multiplicity. So for example, A of 20 is 2 plus 2 plus 5. And the 2 appears twice because 2 squared divides 20. So in the 70s, Aladi and Erdős wrote a paper about various properties of the function a of n, and there are many theorems in the paper. I'm extracting one result. I'm not claiming this is the most important result in their paper, but this is the one that's relevant for this talk. So one of the things they observe is that the function a of n is equidistributed modulo 2. In fact, they prove a quantitative form of this result. So the left-hand side here, the sum of -1 to the a of n gives the difference between the number of times a of n is even and the number of times a of n is odd, and they prove that that's quite small. And the way they do this is they reduce it essentially to the prime number theorem. This function -1 to the a of n is actually fairly closely related to the Mobius function, and they can use results about partial sums of the Mobius function. Okay, so this is just a of n mod 2. What about a of n modulo other integers? So I'm attributing the next theorem to two mathematicians, so Hubert Delange and Dorian Goldfeld. So Delange actually at the end of the 60s wrote a paper about equidistribution of additive functions. And if you apply the theorem in his paper to the function a of n, you deduce pretty quickly that a of n is equidistributed mod q for each fixed q. Dorian Goldfeld, a few years ago, for a conference in honor of Krishna Aladi, actually looked in detail at the case of a of n and obtained more precise results. So for example, you can see here the number of n's which a of n is a mod q is x over q plus an error term that's big O of x over root log x, where the constant here depends on q. Now, this big O of x over root log x error term is actually best possible if q equals 3. You can get from his proof that it can be improved in certain cases. I don't want to say too much about these results, but I think it's interesting to say something about how they're proved. We want to show equidistribution within the group Z mod QZ. So the natural thing to try is to hit the function a of n with the additive characters of Z mod QZ and look for cancellation in partial sums. So once you hit the function a of n with an additive character of Z mod QZ, you get a multiplicative function, and you want estimates for the partial sums of that multiplicative function. And there are various ways of getting these kinds of estimates. So one of which is to apply the Landau-Selberg-Delange method, and that is what Goldfeld does. Okay, so here's Hubert Delange on the left, here's Dorian Goldfeld on the right. Okay, so A of n is going to be one of the stars of the show in this talk. The other star of the show is Euler's function, phi of n. So phi of n is just the usual totient. It's the number of units in the ring Z mod nz, or it's the number of positive integers between 1 and n that are relatively prime to n. Now, it's certainly not the case that phi of n is equidistributed modulo q for every fixed q. For example, it's an easy exercise to show that phi of n is even once n is bigger than 2. So you're out of luck if you want equidistribution modulo 2 or if you want equidistribution modulo any even number. But in fact, the situation is even worse for equidistribution because one can show, and I've put an outline of the proof on this slide, though I won't say much about it now, one can show that actually phi of n is a multiple of any fixed q almost all of the time. That is, fix your favorite positive integer q, then for almost all n, that is asymptotically 100% of integers n, phi of n is a multiple of q. Okay, so it's not the case that every residue class mod q gets its fair share. The zero residue class is hogging almost all of the values of phi of n. So motivated by this, we might wonder, well, is there any sense in which the values of phi of n could be equidistributed mod q? And one proposal was made by Narkevich. So here is the definition of weak uniform distribution of an arithmetic function. Again, same setup as before. I have an integer valued arithmetic function. I have a positive integer q. I'm going to say that f is weakly uniformly distributed modulo q. If, well, first there should be infinitely many n, where the GCD of f of n with q is 1. So f of n should be coprime to q infinitely often. And then for every integer a that's relatively prime to q, the proportion of n for which f of n is a mod q, taken out of all the n's for which f of n q is 1, that limiting proportion should be 1 over phi of q. So weak uniform distribution is like uniform distribution, but I'm just thinking about the n's where f of n is relatively prime to q. Okay, so phi of n was certainly not uniformly distributed modulo q, but maybe it's weakly uniformly distributed modulo q. Now, we only have a shot at this if q is odd, because again, if q is even, then this condition that phi of n be relatively prime to q infinitely often will not be satisfied. So if we hope for weak uniform distribution, we have to assume q is odd, but that's not enough either. So you can analyze phi of n in residue classes modulo 3 by, for example, the Selberg-Delange method, and you can show that the number of n up to x for which phi of n is 1 mod 3 is asymptotic to a certain constant times x over root log x as x goes to infinity. And the number of n up to x for which phi of n is negative 1 mod 3 is asymptotic to another constant times x over root log x. And the thing is, these are different constants. So the first constant is about 0.6, the second is about 0.3. So if you're interested in this, you can see a paper of Dents and Pomerantz where they actually work out more explicit values for these constants. But the point for us is that these two are not the same, which implies that phi is not weakly equidistributed mod 3, and that in turn implies that phi could not be weakly equidistributed modulo any multiple of 3. So the only possibility, if we're hoping for phi to be weakly equidistributed mod q, the only possibility we can hope for is that this holds if q is relatively prime to 6. And Narkevich showed that that is indeed the case. As long as q is relatively prime to 6, phi of n is weakly equidistributed mod q. Okay, so there's a little bit on the slide about what goes wrong with q equals 3. I'm not going to go into that now. But again, I want to say something about the approach. And the approach is very similar to the approach that Delange and Goldfeld took to study equidistribution of A of n, or equidistribution of arithmetic functions. Now we're looking at a multiplicative function, and we're looking at coprime residues. So the natural thing to do is to hit the function with a multiplicative character mod q, that is a Dirichlet character. And you would want to show that when you start summing chi of phi of n, where chi is a multiplicative character, that you get cancellation, where now the cancellation is with respect to the sum you get if you use the principal character. Okay, and well, Narkevich did this. This follows from what would now be thought of as a special case of Pollack's theorem about mean values of multiplicative functions, though he was able to get away using an earlier result due to Viersky. Okay, so all of this has been a summary of past results. I want to move on now to the purpose of this talk. So I should say that I've just given you two examples. The examples have been of the function a of n and phi of n. And of course, you could ask the same question for many other arithmetic functions, and the same methods apply in a great deal of generality. So there's, again, work of Delange and Narkevich about this. But all of the generalizations that are in the literature so far seem to be working in what I'll call the F aspect. So they're interested in proving weak equidistribution theorems for wide classes of functions F. And what I'm interested in is, well, what about the Q aspect? So can we prove these kinds of equidistribution or weak equidistribution theorems where your modulus Q is allowed to vary with the stopping point of your count X? So, of course, this is a familiar thing to do in number theory. The primes are weakly equidistributed mod Q for each fixed Q. That's one form of the prime number theorem for arithmetic progressions. But in many applications, it's convenient to know this not just for each fixed Q, but to know that you get asymptotic equidistribution in coprime residue classes mod Q as long as Q is not too big. And we do know this. So the Ziegle-Voltfish theorem says that you get asymptotic weak equidistribution in coprime residue classes mod Q as long as Q is bounded by a fixed power of log X. And so the natural question is, okay, do we have this sort of uniform equidistribution for, well, uniform in one sense, but uniform also in the modulus? Do we have that for things like a of n and phi of n? And the theorems that I'm announcing today, joint with Akash, are yes, we do. Okay, so here are the two results, which I'll say something about. So the first theorem on the slide says that a of n is equidistributed mod Q for all Q up to any fixed power of log X. And the second theorem says that phi of n is weakly uniformly distributed modulo Q, again, for all Q up to a fixed power of log X, subject to this necessary condition that I mentioned earlier in the talk that Q and 6 are relatively prime. I want to highlight that if you assume the modulus Q is prime, then we had this result a little bit earlier. This was joint work with both Noah and Akash. Okay, so yeah, the main theorems I'm announcing, and this all has to be written up. We hope it's correct, but we're in the process of writing it up. Is that, yeah, you have something like a Ziegle-Voltfish theorem for these two functions, a of n and phi of n. Okay, so I want to say in the rest of the time I have something about how these results are proved. And the first thing I'll say is actually what we don't do. So unlike the results I've mentioned so far, we don't use characters to prove uniform distribution. So that kind of approach, which reduces the problem to understanding mean values of certain multiplicative functions, it works very well for fixed Q. It gives you not only uniform distribution, but if you apply the right method, you can sometimes get out things like asymptotic series. But if you're interested in letting Q vary, then it doesn't seem like it's the right approach to the problem. The dependence on Q is unfavorable for us, at least the way we were applying the methods, the dependence on Q was unfavorable to us. So instead, we use what could be thought of as a quasi-elementary method, which was suggested to us by work of Banks, Harman, and Sparlinski. So there's a paper of Banks, Harman, and Sparlinski where they look at the largest prime factor of n, and they prove that that is weakly uniformly distributed modulo Q in a wide range of Q. And we are able, with some work, to adapt their argument to our settings. So let me say more about what goes into this. So I'm going to give an outline of the proof, and I'm just going to talk about the function a of n, which is the simpler function to talk about. And actually, I'm going to make things even simpler by restricting to thinking about uniform distribution of a of n mod Q, where Q is odd. If Q is even, the theorem is still true, but there's one extra complication, which I don't want to get into. Okay, so I'm going to say that this uniform distribution theorem has an initial reduction step, where, as in many arguments that Paul Erdős was fond of, we simply discard n that are inconvenient for us. So let me say what I mean by inconvenient in this context. I'm going to introduce a function, I'll call it j or j of x, which tends to infinity very slowly. For our purposes, j can be the integer part of triple log of x. And I'm going to say n is convenient if the j largest prime factors of n are all pretty big. Here, pretty big means they're all at least what I'm calling y. Y is e to the square root log x.
I'm guessing that you need j to be at the very least substantially smaller than log x, right?
Yeah, I think we want j to be smaller than log x. But yeah, actually as you probably are getting, any j that goes to infinity slowly enough would work for us. We need to, j can't be too big, but it can be very small. So I could have chosen j to be floor of quadruple log of x. But yeah, just for definiteness, I've written down floor of triple log of x. I think we could not get away with double log of x. Okay. So that's j. What about y? Well, the reason for choosing this y is because we know the Ziegle-Voltfish theorem. And the Ziegle-Voltfish theorem tells us that once you get past y, the primes are very regularly distributed in coprime residue classes mod q in the range of q we care about. So for q up to a bounded power of log, the primes past y are essentially regularly distributed in coprime residue classes mod q. Okay. So what does the reduction step reduce to? Well, as I said, we have supplementary arguments which show we can just forget about inconvenient n. And we reduce the problem to proving the analogous statement about convenient n, that the number of convenient n up to x, for which a of n is in a given residue class modulo q, divided by the total number of convenient n up to x, is asymptotically 1 over q. Now, for convenient n, it would be easy to show that almost all numbers up to x are convenient. And so this statement that I've written, this proposed asymptotic, it wouldn't change the statement if I had written an x in the denominator instead of this more complicated seeming number of n up to x such that n is convenient. That would be the same statement that I want to prove. But actually, I prefer to leave the ratio on the left-hand side exactly the way it is. And the reason is that the method we're using actually doesn't require a very precise estimate for the denominator. What we'll do is we'll end up somehow directly comparing the numerator with the denominator and showing that that is asymptotic to 1 over q. Okay, so in order to get this started, I'm going to write n as its j largest prime factors, p1 through pj, times whatever is left over, which I'll call m. And then the sum of the prime factors of n is just the sum of the prime factors of m, along with the sum of the primes p1 through pj. And now I'm going to use this decomposition of n to estimate both the numerator and denominator in my ratio above. So let me start with the denominator. How can I write the number of convenient n up to x in terms of m and the p's? Well, the first thing I'll do is I'll call it capital N. Okay, that's not accomplishing anything, but I can do it. Then I'll write it as a sum of ones. So the sum of 1 for every convenient n up to x. That's still not really accomplishing anything. And then I'll rewrite this sum of ones using my decomposition as a double sum over m and tuples p1 through pj. And the conditions I want on my tuple just say that p1 through pj are the largest prime factors of m times p1 through pj, the largest prime factor of n. They also encode that all of the p's are bigger than or equal to y, which is another requirement of a convenient number. And the second line, p1 through pj less than or equal to x over m, that's needed so that the final number n, which is m times p1 through pj, is less than or equal to x. So I've written the number of convenient n's as this double sum. Again, I'm not really doing very much, but we'll see that this actually is useful in a second. Okay, so now let me turn to the numerator and let me try to write that as a double sum in the same way. So now I want to estimate the number of convenient n's up to x, which a of n is in a given residue class modulo q. I'll write that as a double sum on m's and p1 through pj. And now what are my conditions on p1 through pj? Well, I want the same conditions I had before. So the first two lines at the bottom of the slide are the same as on the last slide. But now I need A of n to end up being congruent to little a mod q. And that tells me that the residue classes of P1 through Pj have to be such that when I add them up mod q, I get little a minus capital A of n. So in other words, what I need is that P1 through Pj, that tuple of primes reduced mod q, is in this set that I'm calling V of m up at the top. V of m is all the j tuples of coprime residue classes modulo q, which sum to my target being little a minus capital A of n. Okay, so I've rewritten the numerator in a way that looks a lot like the denominator, except my condition on the sum is a double prime condition instead of a prime condition, with this extra restriction on P1 through Pj mod q. That tuple has to lie in this set of coprime tuples V of n. Okay, so the top of this slide is just what was already there. And now here is actually the meat of the argument. The Ziegle-Voltfish theorem says that past y, primes are essentially equidistributed modulo q. And all of the P1 through Pj are primes past y. And so by carefully applying Ziegle-Voltfish, you can show that this sum on P1 through Pj with a double prime condition is essentially the same as the sum on P1 through Pj with just the single prime condition, where the extra congruence conditions on P1 through Pj have been stuffed into a factor size of V of m over phi of q to the j. Where does this factor come from? Well, phi of q to the j is the total number of possibilities for a j tuple of coprime residue classes modulo q. And the size of V of m is just the number of j tuples of coprime residue classes modulo q that P1 through Pj are allowed to occupy that are good for us. So using the equidistribution of primes in residue classes, I can replace the double prime condition with a single prime condition with the size of V of m over phi of q to the j now on the outside of the inner sum. And now here is the kicker. What is this proportion size of V of m over phi of q to the j? Well, this can be estimated by some fairly straightforward combinatorial and additive number theory, some fairly straightforward CANT. One finds that no matter what m is, the proportion of coprime residue classes which sum to what we want it to, so little a minus capital A of m, that's always more or less the same. It's always 1 over q. What's going on here is that if you start taking coprime residue classes modulo q, picked uniformly at random and adding them up, it quickly becomes uniformly distributed within the entire group Z mod QZ. And so this factor, size of V of m over phi of q to the j, is always about 1 over q, regardless of what m is. And this allows me to take 1 over q outside of the sum. I'll just pretend size of V of m over phi of q to the j is literally 1 over q. And then I find that the right-hand side of this middle display is just about 1 over q times the sum on m's of the sum on P1 through Pj, where the inner sum is just the prime condition now, not the double prime. But this double sum on m and P1 through Pj with the prime condition is just exactly my denominator. So I get 1 over q times n as an approximation for my numerator. The numerator is about 1 over q times the denominator. Numerator over denominator is about 1 over q, and we're done. Okay, so that is a sketch of the proof. And I will say that, as I said, there's also a theorem for phi. The theorem for phi follows the same general plan, but the estimates are a little bit more complicated. As one might expect in this business, you end up using tools from the anatomy of integers, and you end up using some tools of sieve methods. I just want to highlight one ingredient that goes into the argument for phi. In the phi problem, the denominator is the denominator in the ratio we care about is the number of n up to x, which the GCD of phi of nq is 1. Now, as I said, because we're doing this kind of comparison method, we don't need extremely precise estimates for the denominator to make the argument work. But there are error terms which were completely suppressed in my sketch. And to handle the error terms, you do need to have some estimates. They don't have to be incredibly sharp, but you need something. And actually, Scourfield in the mid-'80s already estimated this denominator quite precisely. And her work is more than enough for what we need to carry things through. Okay, so that's it. I want to say thank you. And I welcome any questions.
Thank you very much.
Yes, I have a question. The Ziegle-Voltfish Theorem seems to play an important role in your estimates.
Yes,
I'm
that's right.
wondering whether you guys have formulated the problem differently so that at the crucial point, you can use the Bombieri-Vinagrorov mean value theorem for primes. I mean, it significantly allows you to replace bounds on Q by powers of log of X by actually powers of X. And I'm wondering whether you guys have considered that.
Oh, so using Bombieri-Vinagrorov, I should say we haven't considered it as much as we'd like to. I appreciate the question. So we thought about that sort of thing a while ago, but that was all before we had these arguments. And I think what you're suggesting is very reasonable now to revisit that line of inquiry. So yeah, I guess the answer is no, but thank you for the question. And yeah, we'll think about it.
All right, thank you.
Other questions for Paul? If not, we thank him again for his very nice talk. And our next talk, I hope, is in 5 minutes.